has been doing theory, right? So we'll review the theory very briefly, and then we start doing data. So that's sort of what I'm generally doing this class. Sometimes a little more theory than usual, and on other sections, but this section will be very short because you know this stuff. Right, so let's maybe just review. The material comes from this book. Right? So that is Empirical Finance for Finance and Banking by Solis, Dr. Solis. Well, that's very applied. There is that's sort of very big theoretical sections. There is reviews of them. All right. So what are regressions? What is co-integration? What is unit testing?
Cũng nó cũng hay lắm mà.
But also when it talks about applications, apply basic stuff, and that is what I use. So MPT I'm taking from this. Well, you can also borrow my books in case you need them. So you can take them, have them with you before I fly home, and I would like to have them. So let's start. With the portfolio theory asset allocations, so there's one of them, the money, and then we talk about asset pricing models, factor models a little bit, and then talking about market conditions. So the three topics of it. So when you need factor models, I need to estimate the compound for each factor, 5 factors for you, so I will review them. And then sort of here too, but I mean the focus will be more on sort of how to use them for your sort of portfolio applications. Are they useful section for I will talk a little bit about market efficiency of that section. But let's see how far we get today. Well, of course you know what is MPT, so we started with work of Markowitz, 1952. That's an old paper. It's very easy to download it and read it. And that's sort of very old. But it still is very important in the sense that it has a big effect on the risk. So the understanding that we brought was so basically, I mean, his point was that if you have asset returns and they are interrelated, right, then sort of you can use diversification to reduce the portfolio risk, but then it will never become zero. Right? So you can reduce it, but you cannot eliminate it totally. Right? So it doesn't really work. Right? So good money. So what actually happens is that, well, let's see sort of the line of logic of this guy. When he says, okay, but investors are interested in the returns, right? And well, at times they don't like risk. Right? So that's sort of two. So you like the first moment, you don't like the second. Right? So that's sort of, you don't want the second moment to go off. Sort of, then one has some opposing needs, and then one has. What do you hide your food?
Just to clear the table for me.
Yeah, otherwise it can't work. I'm the same. When I work, then I need my table to be clean. Otherwise I can't see it. Quite easy, yes. Wherever you So, well, then you have this opposing indeed interest. So more interest, more expected returns, less variance. So that's sort of what we have here. And but these are quantities which we can generally estimate. So we have learned how to estimate. They are oftentimes not so easy to estimate. So well, returns are simply averages. We have some theory. We need some sort of stationarity in some sense, and we can estimate the asset returns. Otherwise, it's something which is not relevant. We're not really representing the true asset. That's not relevant. The other basic issue that we have is that when you come with covariance metrics, if you you have two assets, then it's somehow easy. If you have three, it's also not a problem. Right? So that's sort of not a big deal. But if you have 30, 50, 100 assets, it becomes tricky. Right? To estimate basically the covariance. So these are important. So we have the return and the covariance matrix, so we have to be able to estimate. So numerically, covariance matrix estimation is hard. It's not an easy task. So one needs some structures. One needs to think. One needs to actually think of the problems that the covariance estimation has. How big the bias is, essentially. So we may have a big bias in the covariance matrix estimation. So as such, there is a large literature that has been devoted into this simpler covariance estimation when the dimension is large. So that's sort of one important aspect. And then, when it comes to sort of this covariance mean combination, then you need these inputs, and then you have to be able to estimate the problem. Well, in any case, so as time passed, the Markovics started to think a little bit further, and then thought, okay, let's somehow take it for granted that we can estimate the variance and the mean properly. So sort of back then, that's sort of 1959 or 52, then sort of the issues were a little bit different, right, compared to now. Because now we have sort of the frequency at which you trade is higher, you have more data, so there is more problems, so to speak, that we have in your series. But let's see what we have. I mean, of course, they also like sort of, okay, well, there is also a risk-free rate, right? And risk-free rate can help you reduce the risk. If you invest in there, then well, that's risk-free. It's not totally risk-free. But it is actually, the risk that it has is very little, so to speak. And you can invest in it so that your sort of risk comes down. Calculation of the returns, of course, no. Alright. So when you have the percentage changes, you have the dividend, when you add it there. Alright. Well, remember that we have the log returns, the additive. Right? So to speak, if we calculate the log returns, if they are ID variance of n periods, will be n times the variance of one period. So that's sort of what we know because they're additive. Right? That's why I like log returns more. In practice, combines the percentage changes because they're sort of more tangible. In general, but I mean, this is something that we have to talk about. So I don't need to go into details of how to calculate the returns anymore. But of course, we have also a general model for prices in log. Right? One says that the log prices follow a random walk. That's sort of generally one has. The shocks may be a Martin different series, which basically allows us for embedding a large P model in there. So that's not a problem, as long as there are MPS. Right? And this mu is a drift. So if it is zero, then there is no drift. If it is positive, then the prices are on the rise. You have a positive drift. Otherwise, then it is a downward. So when a random walk is a model, then you need to sort of, if you want to say that prices in a financial market actually follow this model, then you need some assumptions. Because that's a model, then you need some assumptions. For example, let's say, well, often one speaks of prices being low now. So if they are, then there's some other assumptions saying information is efficient financial markets. And we talk a little bit more about that when I come to the efficient market hypothesis. Then basically they follow around the board. Right? So when we mean if they're around the board, let's take P to the other side. Right? So then we have log differences of the, so that will be log returns. And log returns will basically follow this very simple setup. So you have this, so if PT is non-stationary, it's a unit constant. If you take the difference, then you reduce the order of integration by 1. no other covariance, any lines, variance may be fixed, or conditional one. And then the mean, which is also like a sum fixed. Right, so these are stuff that you know, they're classical facts. These are also the various motor views, what will happen, ExxonMobil, and General Electric basically returns. We did look at this sort of behavior in this series. That we have some times where things are turbulent, and then the variance is small, so we have this variance clustering, and we did talk about this in the previous basically sections last week. So I don't need to basically talk about that too much. Well, if you have, say, a large specification, then the variance of the returns will be this. So the variance of the shock, which is what we have there, sigma t epsilon t. That will be the variance. The variance will be governed by those parameters. Right? So that is stuff that we have done. So far, so good. So which is sort of interesting. So it means that, well, if there is large specification in the series, or large basically affects, then I go to portfolio selection, then I will need to go on and then do the estimation using some model which is appropriate. Or maybe do, well, we appreciate there is time variation in this variable, sort of the variable, and then estimate the variance using at least a rolling window frame, right? So that we capture the time variation in the series. Right? So that's sort of the point of this slide. Right? So here, and there is time variation in conditional variance, and we actually need sort of do that. Well, that was a bit of very fast review in this last 10 minutes of what we did so far, more or less. Well, of course, so in practice, when you want to invest and you want to know what is the value of this asset, right? And you want to also turn off now. Thank you very much. And yours is on. Okay. Well, I mean, then, so if you have an asset and you want to know is it worth indeed buying it or not, then oftentimes you would want to calculate its present value. So that's sort of what it is. Or so to speak, the intrinsic value of the asset. All right. These are accounting stuff. But let's say you have an asset that sort of produces a cash flow, CF, in the future. All right. And then you have some discount rate K. Right? If you want the intrinsic value of the asset, then you discount all of the future cash flow values to today. Using this. Oftentimes one uses this. Right? And well, it's some sort of a present value model. Right? So sort of you discount all of the cash flow, and then you basically know, all right, so how much this asset is, what is the intrinsic value of the asset? Discounted now. And that's used. Like in practice, one uses it because that's interesting. Sort of, you have an asset in front of you, then you discount all of the future cash flows to today, and then, well, if you have 10 assets, then you can rack them with respect to each other. I guess that this is also killing you. So from bachelor economic accounting courses. So, well, I mean, which also comes in here. Well, so when it comes to stocks, then, well, then the cash flows become the dividends. All right. Right. So that's sort of what if I own them, then sort of apart from the price variation, if I buy them and want to sell them and I earn, but then the cash flow is what actually the asset pays. For example, Microsoft pays nothing. So then that's the sort of what you have here will be looking for the money. Or not using it. But then when you buy it, then the value that you have to give will be also a function of the price at the very end. So you want to keep it for 12 periods, and you could split months, say, or days, I don't know. And then this PN divided by, you have to basically discount it down to today, so you have the value of the asset. Well, I mean, that's the problem. The problem is that when you are at period T, then the cash flow in period N is not known. The price is known. That's a random thing. That becomes a little problematic to evaluate. You have to speculate. Because you have to speculate, then sort of it becomes like a gamble. Right? And not all of the courses that you have had so far in finance and derivatives and blah, 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 because there is a lot of stochastic and deep components. So, well, I mean, let's simplify this stuff. Well, for example, let's say let's focus on the dividend. So, well, we believe the price is off, and then, or sort of do some forecast, at least in very short periods. So if you can forecast the returns, then you can forecast the prices, at least in a very short period. Those forecasts are changes. And if I forecast the changes next period, then the price will be plus the changes will be the price the day after. That's what we do. And well, I mean, in accounting, people actually decide, okay, well, let's have the dividends simplified in the sense that one says that it grows at some certain rate G, and then you get this one that potentially you know. So that one basically gets the dividend at period T with that growth divided by K minus G. So that's the model which is called the working model. Maybe you know that. That's some very simplified assumptions we make, and then we get something which, well, depending on G and K, then we would know what the value to be is. So this cash. Well, that's not this is sort of just, so I just want to focus with this story that you need something to make a decision on investment. Alright. So very rough stuff is this intrinsic or present value calculation, but then they are coming with specific problems, so they are not directly usable when it comes to investment. Sometimes one moves a little bit away from this. That's why we have all this asset allocation stuff. And then because there are stochastic, then you're always worried. Will I get money, will I not get money? So you do somehow you sort of need some performance measure, tells you that whether sort of the rating scheme that you have a certain portfolio brings money or not. And then you have the performance measures. You know Sharpe ratio, right? Or Trainor ratio. Which is Sharpe instead of which is like Sharpe, you have the expected returns in the numerator minus the risk-free rate, not divided by the standard deviation, but rather by the cap and beta. So that's also a measure of risk. This beta is a measure of risk exposure. Where sort of if you take the standard deviation off and put the beta, then you get some other ratio. So I mean, to basically measure sort of the attractiveness of your analysis. So, well, I mean, fundamental analysis is good. If you can calculate the intrinsic value, if the current price is smaller than the intrinsic value, then you invest in it. That's as simple as that. It's somehow very simple. Alright, so that's sort of what we do. So you may go short or long depending on the well, let's maybe a little bit move on and then go to the MBT itself. What is it? What? Is it too simple?
No, because I'm interested in this topic very much.
Yeah.
So I smile.
Oh, so you like? I thought maybe this is so simple and so what is he telling us? So you were happy to. Alright. Well, I mean that was the simplest stuff, alright? So that's sort of the stuff that we don't really do. Alright. So in this class I mean this is not an accounting class. But let's go to MPT, the modern portfolio theory, and that will be the start of the discussion I have essentially today. Well, let's say you have risk neutral investors. They don't care about risk. Okay. Then look, I mean, what I want to tell you is that you have different types of investors. Some they don't care about the risk, right? So they're risk neutral. They are generally younger people. So, but then you have people that are risk averse. Right? So they're a bit older, like I am. And then they have certain goals to reach. For example, let's say, well, I mean, I want to invest somehow in assets to gather some money because later my child wants to become a student at VGU, I have to pay for her or him. And when I just don't have any possibility of risking the money that I have. Right? So, well, I may actually accept some risk, but a little bit less. All right, I'm not risk averse, by the way. so that's very important. Well, I mean, then if you have risk neutral people, then things become simple. They don't care about the risk. Then you look at the returns. So say Amazon creates more return than I will buy, well, compared to BASF. BASF, the chemicals, the big, one of the biggest in the world in Germany. You know that probably. Wait a minute. Is there anybody of you that does investment? Like you do? Oh, very nice. Okay. So you own assets, or you buy stocks. So what do you do? You have an ETF or mutual fund? Mutual funds. You own it. It's, what is it that they ask?
This is called Viet Capital.
Viet Capital. Yeah. This is data available of this. You can analyze your portfolio. So what do you have? And that's sort of, you just have this stock. So that's an index you bought.
I don't directly want it, but I give them the money and then they.
Oh, so you went to a broker, somebody?
Yeah, I don't. I just put it in an account. I also have an account, put money in, and then we buy.
Does it pay?
Yeah.
How much? 10?
From the tax from it's go up from about 35 saving now it's go up to around like 5%.
Why first?
From the agreement the president so
That's very nice. So that's sort of what we basically have. Right? So we look, right? So that's sort of what the Visa stock seems to be paying good. Right? So it's sort of on the rise and you go buy it. Well, that's sort of nice. Right? So you focus on the return, not the risk. You don't know the risk.
yeah I don't care about this.
You don't care about the risk. So the risk is
Honestly, I say I'm a risk lover because when I see some stock go down or there's some opportunity for me to buy.
alright. So that makes sense. If it goes down, then you buy it. So it will go up. But maybe it goes more up, more down. But then you wait.
But I don't directly analyze it. I have some, yeah, exercise, we have some exercise people who analyze it only, so.
That's very nice. So you don't do that. You don't do the analysis, you don't care about the risk, more or less, right? Specifically the investment that you have now, you just look at the return and then you just see it. That's nice. What you can do, you can become different. So sort of, if I understand this investment strategies, then this is in this category. Yeah. So one period horizon, I don't know how long you want to keep it, but let's say one period, then the investment strategy is clean. Invest in those assets that have a higher return, like this. Right? Of course, you have to be able to calculate them. All right. Well, I mean, the more fun part will be when you have risk neutrality goes off, right? So that people are interested in risk. Right? And then once you buy something risky, then the market gives you a premium because you are nice. You take risk off my hands as a market, all right? And then I pay you. Right? So, which is interesting. So sort of for sort of in this industry. Right? So then, but things become a little bit complicated because so if I'm a broker and I want to sell you some product, well, you say you don't know how this works, so you simply went to some website, put some money, and then they did it for you. Then they pay you the money. Should you pay tax on them? Yes.
No, I don't pay tax, but I pay the fees if I take money out in the proposal that we decide.
And then, sort of when they buy this from you, then you also pay commission, right?
Yeah.
Okay, so that's agreed upon. Sort of, it's part of the contract. Okay. So the broker, you have to pay something, otherwise they don't do this for you, right? Or, well, generally this is sort of the payment that you have, generally is sort of coded in terms of something which is called a basis point, right? So, for example, 30 basis points is 30 out of 1,000. So if you have 1,000 euros, 30 is take off. That's sort of on a certain basis in that period. All right, so that's sort of what we have. But things become a little bit complicated because we don't know the appetite, the risk appetite of people. All right. Oftentimes I have to talk to them. So if I want to put together a portfolio, then I talk to them and I ask you, what do you want to do with this? And then you give me some information and make up my mind. All right. So, and then well, there is a. You have had a course with Michel Aliasus. Yeah. Okay. So I mean, he has this gamma parameter, which is the risk aversion parameter. So he also sort of talks about this, I suppose, in macro. What did you have with him? Money market?
Macroeconomics and households finance.
Okay. So the household finance. So then there is the households, and they have some risk aversion in his utility functions. And then generally we don't know what is it. Right? So I ask you, what is your gamma? Can you tell me? You can't. So that's why we don't know. So that doesn't really work. Then I have to make up my mind. And then given my experience, then I say, all right, so this person has a small gamma or a high gamma. Very big risk lover or a risk averse person. All right? So well, there is no theory to do this. That's an interpersonal stuff. And then well, if you get it wrong, then things sort of may go wrong, essentially. So you not make the person happy with the investment, sort of a strategy that you offer. But oftentimes, because it's not clear, then sort of I may produce different portfolios. All right, so different portfolio, 1, 2, 3, 10, and then you decide. You tell you, okay, so the risk is this, the mean is that, overall horizon 1 month or a year, and then you make up your mind and you say, okay, I want portfolio 5, and then you go on. Right? So you write the contract, I tell you this is my basis points, or this is my fee, and then you go on. Right? That's sort of what we have in general. All right, so that's sort of a bit, sort of a window in real world, very brief. But let's see, what is the MPT assuming? Because that's a model, sort of academic, all right? So here the assumptions are that we have a one-period horizon. If you have multiple horizons, then it's not a problem. You have to always take into account that after one period, then things may be reshuffled, so you have to pay some more fee. Well, I mean, then you have to sort of bring that in. Right? So whenever you have more than one period, then things become a little bit different. Right? In terms of calculation, so there is a commission that you have to pay, sort of for, because there will be some transactions. Because the contract finishes, and I have to now write a new one. So, but let's say that we have, so that's a simplification assumption. And then, so investors are risk averse, all right? And maximize utility, which is a positive function of the expected return. All right, so that's sort of what we have. Well, they're not risk neutral, they have some risk aversion. They have some risk appetite, but it's not that they are zero risk interest, but then that's sort of what we have here. And then when investors quantify a risk using the variance, right? That's again a simplification assumption. Right? Because sort of how do you measure the risk? Do you use the variance to measure the risk, or you have some other sort of risk measure? Because that's not the only one. What other risk measures do you use? Apart from the variance. Well, kappa beta is one. Yeah, it's another one. So two. Number three.
Systematic risk.
That's right. Okay. So we have systemic and systematic risk.
Industry related risk.
Very good. Okay. So there's sort of some risk that we have there, but that's true. So that's the source of the risk. But my question was, how do you measure the risk? How do you calculate it? What do you give me as a number? All right. So you can use variance of the returns to calculate the risk. It doesn't matter which industry you are, right? What you have, or you can calculate the kappa beta. All right. Or you can calculate value at risk. That's another one. Or you can calculate expected shortfall. This you know. Expected shortfall. That's a good topic for your master thesis. Alright. Let me tell you what is value at risk. You should do your master in finance. Maybe you should read. It's very full stuff. Alright, so let's say you have some distribution like so, looks like normal, okay? And then, well, I mean, it has quantities. Let's say the 95%, let's say here we have 95%. If it is a standard normal 0.01, then this is 1.96, you know. And this is minus 1.96, you also know. Let's say these are the returns. Right, so the returns have this distribution, simplified distribution. Right? What is the probability that you end up with a return smaller than minus 1.6? That's true, exactly. Right? So that's sort of the, well, this is a quantile, right? That's a quantile of the distribution at well, I mean, I don't know, sort of, let's say 975, right? So that's sort of what we have. So that the area to the left of it is 975, this one. Right? So that's the 2.5% quantile, right? Well, it means that sort of, and now let's say you have the returns of period T look like so, and then tomorrow they also look like that. So what is the probability that you have a return below this tomorrow? Then of course it's 2.5. All right, that's what we have. Okay. So, but let's say that you own the stocks which are worth 1,000 euros. Well, that's very small. So you have something which well, the value of it is 1,000. That is what we have. And so So let's say we calculate, so I want to basically calculate value at risk at is 2.5 of basically these assets that I own, essentially. All right, so that's what I want to do. All right, right. So, well, so that's what I have. And then, sort of these are the stocks that I own, the value, the prices. All right, so let's say what I know. Let's say I have 10 stocks, each worth 100. All right, 10 I have, each is worth 100. And then here I have the returns of them, which is normally distributed mean zero variance 1. Right? Or let's say variance 1 as it is. Right? So the returns that I get on these is 10 times the return of one individual asset. That's sort of what you have here. So, so tomorrow I may lose, right? So the prices may go down, or I may earn. That's what I basically have. Right? So, what is the probability? Or whatever, let's say, well. So that's sort of that is what I have tomorrow or today, and then there is plus some return. So return on the portfolio. Let's forget about 10 times 100, or rather this is the return on the portfolio. Right? So, well, and then tomorrow, well, and then the mean will be essentially, well, 1,000, all right, plus what happens tomorrow with respect to these returns. All right? So that's sort of what we have. So that's the return that I'm getting. Alright. So can you tell me, if the returns tomorrow is -2, alright, then how much do I lose? Then maybe you take the pen and then do some calculation. Calculations, alright. So let's look at this like that. Let's say you have some asset which is worth V. So V is the value of what you own. I want to calculate the value at risk. Let's say a certain level. Alpha. Alright. Right. So that is what we have. Let's say alpha 2.5%, then it is corresponding, if I believe that the returns are normally distributed with mean 0 and variance 1, then they will look like this. Let's say I have the returns that I know that they are normally distributed with mean, say, mu, or let's say 0, but generally the returns are 0 mean in the market. And then some variance which is sigma squared. Well, and that is what we have. The value at risk at alpha percent here for 1 day. The generally value at risk is, well, has 2 characteristics. First, the percentage at what level to calculate the value at risk, and then over how many days. Right? Well, let's say we take T days. will be, well, I mean, this is z of 1 minus alpha, alright? Generally will be negative value, alright? And then here you have minus z of 1 minus alpha, or you can directly use z of alpha, alright? So times the variance, well, that gives me the quantile of the distribution of the returns, right? Well, I mean, if I basically have t days, so that is t day value at risk at alpha, then, well, I mean, if these are the log returns, then the variance will be t times sigma squared. So the variance, well, the standard deviation will be square root t, right? Times the value. Alright, so that will be the value at risk at for t days at the level of alpha. For example, let's say we said what, alpha to 99. So let's say 90. So I want to 99% 1 day value at risk. Right, so 1 day VAR at 95, at 99%. So then that will be essentially minus, well, z of this is what? So that's 1%. That's 2.3, right? Or 18.
Two one three.
2.3, right?
Yeah.
2.3
Three.
cube, yes. Right, so 2.18 is another. And then here we're gonna have minus becomes a plus, 2.326, right? 1 day, well, let's say standard deviation is whatever value, alright? That is square root of 1. So that becomes the 1 day value at risk. That's the scale. If I multiply it by the value, then I will have, well, that's sort of how much I will essentially lose if I have well, I mean the series, right? So that's sort of what that's daily multiplied by the number of the days, right? And then we will have the value of this. Alright, so that's sort of what. But oftentimes this is standard deviation, well, but the 99% actually, so that is how much of the value that you have is at risk, right? So that's the, well, that's the amount of money that you may actually lose, so how much your basically value can go down tomorrow, right? Well, let's maybe give you an example. For example, let's say sigma turns out to be 2%. 2% means, say, something like that. So, I mean, oftentimes one doesn't talk about the levels, like so, but then one says 2%, and that means the standard deviation is large. Now, let's say I want to calculate this, alright? And then I own 1,000 euros. Alright, so that will be 1,000 euros 1 day times 2.326 times 0. Alright. Then I will know how much of my value is actually, do I actually do the calculation correctly? Yeah?
Yeah.
Well, you have done it probably before. And then I get some number. What would it be?
46, so it's 52.
46. 0.50. Alright, so the value at risk that I have is this. So there is some chance, and that's 1%, that I may be losing this much tomorrow. So value at risk is actually an important measure, right? So you know Basel. You Basel, the bank regulation. All right, so Basel have sort of different versions. There is a Basel 1, there is a 2, and then there is a new version which is 3. Right? So actually Basel 3 uses value at risk, or suggests, that's binding, for banks to calculate the value at risk. All right, so historical value at risk. And they use actually 99% value at risk. And I don't know, I don't remember exactly, but there is a number of times that the banks are allowed to have values, well, actual values below this value at risk level. Right? But I don't know how much is it. So, yeah, so that's sort of the breaches that they have. It's restricted, so they cannot have too much risk. So what they are holding cannot actually go too often below this 99% value at risk in Basel III. Right? So that's an important measure used in the industry, and that's a quantile. Simply, that's the worst situation you can have. Right? That's sort of the 99% is very bad in this situation. So here, for example, well, let's say you have returns that they are normally distributed with, say, mean 0 and variance, which is this. All right. So what is it? Well, I mean, now, well, the 99% quantiles that this guy has, all right, will be, well, sigma times, say, 2, 3, 2, 6. Right, so that's sort of what it is. So if I draw the distribution, so let's say that this is the return. That's mean 0. So these are these returns. Right. So this point that multiplied by this. So let me say some number here. So 0, 2, 3, 2, 6. So the probability that the returns actually are below this is 1%. But that's the 1% quantile information. And that's sort of the constituent that we have for value and risk calculation. The value and risk is indeed a measure of calculation of risk because that quantifies the worst scenario that you have. So far, so good. Well, let's look at the. That's sort of well, in practice, first of all, things may not be normal. All right. So that's an assumption that we make. We assume that things are normally distributed. Well, oftentimes we say that they are conditionally normally distributed, so that becomes the arch-gauge assignments, type exercises. If the variance actually changes, then this becomes time varying. And then if I use the gauge, then I can also forecast this. So I can basically say something with the variance tomorrow. But this is actually one of your exercises or assignments that I posted on my last week. Maybe you should take a look. Because that's an interesting thing. I also wrote a little bit about assignment. Alright, so that's sort of what we have with respect to that is value at risk. Right. But then, well, that is actually called the normal approach. Alright. Alright, so that's the normal approach. So you assume normality, then the value at risk calculation becomes based on the normal. Right. Well, there are other approaches. Let's wait for that. So let's look at the expected shortfall, because that's also another important measure for calculating the risk. Right? So, but let's again go to some distribution. I don't care what, maybe normal, maybe not. But let's say we calculate the value at risk at alpha. Right? And that is R. These are the values of R. So we sort of, we take alpha and we calculate value at risk. these are the estimated density. You know how to estimate the density. Right? And then you can calculate this area. That's from this point. Or that's a simple quantile. Right? So from the data then you can see how many observations. That's a simple quantile that you can calculate from the data. Right? So that's not hard. That's value of this. Let's say you do the estimation using simple quantile calculations. Now let's look at the expected shortfall. So expected shortfall also has a level alpha, but that's the expected value of R for those values that are below here. So that will be integral, so the area that you have here. So that will be this, the area times R. So that will be from minus infinity to value at risk, alpha, right, of R, the PDF. Alright, that becomes the expected shortfall. So if I want to calculate this, then I have a little bit of well, I need to do a bit of calculus. All right. No, well, this is some other stuff. So minimum, not the area below the curve, but that is the cumulative. That's a different story. So that will be 1 over 1 minus alpha, where it's alpha is 0.99. The integration of alpha T1 of value at risks at different values of U, D. So what was the difference? What would be the expected value? And what is that? What doesn't matter? Well, I mean, that is the expected shortfall. So, well, I mean, let's say I have 0.99, that will be the alpha level. When I calculate the value at risk over all of the alpha, from 0.99 to 1, alright? And then do an integration, so calculate, accumulate all of the value at risks. Alright, so for this value, this value, and so on and so forth, and I go on. Well, I mean, because that is one, then, well, I mean, the tails become sort of important. You have to go to the very big negative in the values. So if you assume that R is normally distributed, alright, so there is a very neat, you can do the calculations actually. So if you assume that this is indeed normally distributed, then the expected shortfall will be turning out to be, let's say that has a mean mu and variance sigma squared, then this will have a neat expression. So let me just get it back. That will be mu, so that's the shift that you get. So on the normality, plus sigma times the PDF evaluated at Z of alpha. Alright. The PDF That's also a measure of risk. It accumulates all of the value at risks up to alpha. Right? So that's sort of what we do. So that is very right. And that's the expected shortfall. So that's another measure for risk. Right? So value at risk and expected shortfall are indeed widely used. They're interesting in quantities when it comes to the calculation. Maybe you can check this for yourself. Right? So that the value at risk is a quantile probability. Right? Then take an integration, you should get that. So that would be integral over the CDF of a standard norm. Right? And all of these are compact. All right. Well, that's expected short. To now maybe define an exercise. So you can estimate value at risk that I've done, I will add the expected short. Maybe I should do them later. Try them yourself, and then the next days then I will do the program. Alright. So now we know variance, we know kappa beta as a measure of risk, we know value at risk, number 3. Number 4 is expected short. There is another one. Well, let's say I have a pension. I'm old, 70 years of age. So, and what matters for me is essentially how much, let's say you have, say, the prices, the Zoom price, they look like so. The prices go up and down over some time period. Right? When, that's sort of more anecdotal and joke-wise. Because I'm old, I don't care too much about this stuff. What I care about is the peak, so much money. Right? And then I lost a lot. Right? And this distance for some people matters. Right? Well, so the distance between a peak and a fall. All right? Well, that's also that is like a range. Right? Well, so over some time period. That's also another measure of risk that one can sort of focus on. Well, I mean, that's sort of what we have as a measure. And that is the downside risk. So here, well, let's say you have a peak, and then you have a trough, and then you say, all right, so peak minus trough divided by, so we should normalize it so that we have essentially a value between 0 and 1 divided by the peak. So that would be a number between 0 and 1. When, so if the trough is very small and peak is very big, all right, then this will be closer to 1. If peak and trough are not too far away from each other, then they will be closer to 0. Depending on the peak. There's also another measure of risk, which looks at the extreme values or the range of the data across time periods. Oftentimes one says that pensioners like this more than the others. So, are you now, well, we now you know measures of risk a little bit better. And not only variance, but then there are other stuff. Well, so far so good. And that is a still active research area, even by now. So sort of how to estimate this, because that's a very ugly thing. Or how to understand whether the estimation that you have is good, so to speak, back test. Back testing this is not an easy task. Because that's an integration over the tails of the distributions. And then the tails, we have very few data. So estimations of this is not easy. It's associated with a lot of bias. So it's not an easy task. The expected shortfall. All right, so far so I told you measures of this. All right, good. So let's continue with the other assumptions. So this MPT assumes that the risk is measured using variance, okay, not the others. But we don't care in practice. We can change the value So one assumption, the other assumption of the MPT is that investors have access to risk-free rate. They can go buy bonds. I can buy bonds. Well, I would say in the US, you always have access to the secondary market. So you can always go and then buy bigs, T-bills. That's not a problem. So you can invest and borrow. All right, so at risk-free rate. And number 5 is when you assume that there is no tax. This is what I asked you. You said that there is no tax. All right. And then we assume that there is no transaction costs. But that doesn't matter. So if there is, then you reduce. So you take the transaction cost off what you, well, in terms of some basis points, then you can take them off. All right, so if we basically assume these assumptions, then we can go on and then start our portfolio allocation. Do you have questions before I go on? So let's see what should we do when it comes to the choice between risky assets and then you have a risk-free and so on and so forth. So the first step you should do is to estimate the return and the covariance. Well, let's say you do that. Then we go to the second step, where this could be different preferred risky portfolios. Alright, so here, well, that is the efficient part here. Let's do them. Let's not go on further, but let's do them step by step in Python. Okay. First, I will not do them with real data, all right? But then, so that you see how things are, and then we will continue. I just want to show you how to put together efficient budget. What is that? What is efficient budget? And then we go to ORP and capital allocation line and so on and so forth. So we can go on, and then we go to step 2. So then we get it right. You have not done these calculations before, right? So you have not, so you know what is a, so the question is, do you know what an efficient frontier is? You have not, but put it together. You have not made it up by yourself. You have?
No.
Okay, so that's sort of what we then do. So we do add something to what we do. I thought if you have, then I could do more other things. So why should I keep you busy with this? Let's start. This is sign page, you don't need it. Well, let's import numpy as NP. Let's import our beloved matplotlib by plot as plt, rc params, params, and we go to figure.ptr. Actually, I should change it in the back of it. Now, for simplicity, let's say we have just 2 assets. So that's sort of simple. And I don't go to the estimation, but let's say I know the returns. So I know the returns, one pays me 50, the other pays me 10, and then the risk-free rate is 6. I'll just put that like that. So 6% is the risk-free rate. What is the risk-free rate here in Vietnam?
2.86.
Okay, so that's very nice. Very good. So I just put these numbers. I take them from the book because if you read the book, then you will see these numbers. So that will be who is doing the stuff in MATLAB. I do them in Python. And let's let's say we also have the standard deviations and the covariances. So the variances and the covariances. So the first variance, the second variance, and they are 500. Well, they're big numbers, but that's okay. And then the covariance is positive and is 100. Right? So just have these numbers. But later we will use this stuff. Now, well, look. So here what I want to do, let me mark those. Well, here we have a portfolio. And then the portfolio has some returns, which I call it RP. So this is the portfolio returns. And the portfolio returns, well, I mean, let's say W1 is the rate that I give the portfolio 1. So the portfolio return that I have will be how much I earn from the first plus how much I earn from the second. All right, with respective rates, W1 and W2. Well, in practice, and these are random variables, but now I have the means of them. 10 and 15%. That's sort of the portfolio basically return, right? And so then the portfolio there also has a variance. All right? The variance of the portfolio is variance. Well, so that will be the first. Remember, right? So that's a linear combination. Sigma 1 squared plus W2 squared, sigma 2 squared plus 2 W1, W2, sigma 1. That's the variance of the portfolio. And they depend on these weights. Right? Now, well, you could choose 1 here. So it means that you will earn 15% and then 0 there. And that will happen to affect the variance. Right? Well, look, I mean, if I'm risk averse, sort of risk neutral, then I will ignore the covariance and variance and then go invest all of my funds in the first one. Right? Otherwise, then I will, well, sort of have a different risk. Right? So now, well, is W1 plus W2, well, let's say we set them to add up to 1. And then we basically say that they are positive. Right? Well, now we have infinitely many ratings that we can have. So for each weight, then you will have some return and some variance. Right? So to speak, each of the choices that you make gives you a certain return and a certain variance. Right? So it means that we have a choice set out of these W's. Right? So, and when it generates them, they generate the potential rates. And let's say,
Professor, that is the standard deviation, the 500 to 250.
these are the variances.
The variance, I have to be devoted like the answer. I thought that it's
Oh.
it's a little bit big.
Let's call them sigma, well, I mean,
Sigma, oh, okay.
so these are variances. Right? So variance and covariance. Variances and covariance. Right? So we know this is not the standard deviation problem. Alright, so now let's generate the W1. Alright, so W1, well, let's say we have a range. So that's a non-point. So that is a range of, well, let's say this starts at 1 and goes to n plus 1, and then we divide it by n. Right? So then the first weight will be 1,000. Then 2 divided by 1,000 till 1. That will be the last. Alright? So that's W1. And then I know what is W2. Alright? So that is 1 minus W2. So let's then, well, these are the weights. Simply they add up to 1. So W2 is 1 minus W1. Okay. Now I can calculate the return.
So this is like anything doesn't have the actually rate
I could use a range, yes. You wanted a range. We can, right? So that is not a difference, right? So that's just a range, right? So. Oh, you mean, oh, yes. So it should be a range, not a range. That's you're right. So that would be a range starting from 1 and going to, well, thank you very much. But let's calculate then the returns of the portfolio depending on all of these rates. That will be R1 times W1 plus R2 times W2. Alright, so let's calculate the standard deviation. I call it not sigma squared, but that is the standard deviation. So that will be NP SQRT. Alright, so I'm not looking at the variance, but rather the standard deviation. So that will be W1 to the power of 2 times S1, so that's the variance. W2 to the power of 2 times S2 plus 2W1 times W2 times S1. Right? So these are the rates. Okay. Well, let's just run it. It seems to work. Alright, so these are everything. Now let's do a plot. Alright, so I will do a scatter plot. Alright. On the x-axis, I will put the standard deviation. On the y-axis, I will put the return. Alright, so PLT dot show. Parentheses close and open. Alright. Well, this is somehow not interesting. Let's make a marker the plot. And then let's set size to 2. So that it's better. It looks nicer. Alright. Look, on the x-axis, then we have the standard deviation. Alright, so here then we have the standard deviation of the portfolio, or let's put it sigma phi. Alright. And on the y-axis, then I have the returns of the portfolio. And that's a standard plot. And this is something you have seen probably before in some of the previous textbooks, right? This is the mean variance. What is it? The efficient frontier, right? So the efficient frontier is the locus of all of the portfolios you can choose from. Alright? So you can choose a portfolio which is here. Alright? So then it will give me, well, here I can check which actually ratings you have. Then we give me a return of, say, well, roughly 10.5 and a standard deviation of 15. Alright? So, well, if I want a bigger return, right, then I sort of go on and then see, right, so where the biggest return is, right, so which is when W1 is 1 and W2 is 0. I may want to have the smallest variance, all right, so the smallest, so the portfolio that has the minimum possible variance, all right. And what do? And I go to the nose. Here, the variance is the smallest. That's the minimum variance. Regardless of the return. I don't care what the return is, but the minimum variance actually takes, well, that will be on the nose of this mean variance frontier. Good. But now, so that was the step 2. Alright, so that is the mean variance. So we have to pick one of those points, which is actually the nicest one. And then let's go down to the slides and then go a little bit ahead. Can I? You have typed it or? Very good, so let's go here. So now, well, these are the preferred risky portfolios. All of them we just drew, and that is the efficient frontier. And then from these portfolios, and using the information on the risk-free rate, we choose the optimal risky portfolio. For short, it's called ORP, optimal risky portfolio. An optimal risky portfolio is in such a way that maximizes some utility. Well, the investor has a utility. Right? So now, now this becomes the numerical part, the interesting stuff that we do. So well, we have a utility function, and the utility function is a function of the return of the portfolio and also the standard deviation of the portfolio. All right, so that's sort of what we have here. But of course, these are a function of the base, right? So we wish to maximize the utility of the investor in W1 and W2. Right? So now, well, I mean, how do we calculate this risk as sort of the utility? Right? So how do we, I mean, we need something that tells us what the utility function is. So, well, I mean, one of the ways that we could put together the utility is to think, well, let's instead of RP and R, well, let's put it that way. So let's RP and the variance. Right? So, well, the investors are interested in more returns. Right? So the function should be positive related with the returns. But of course, they are not, well, sort of they want to know how much do you pay me on top of the risk-free rate. So that's sort of the numerator of this basically ratio. And then I want that this actually, the utility function is a decreasing function of sigma. So when sigma is higher, then you have a smaller utility. Then you can actually say that this is indeed inversely related with the utility, with the risk. All right? So that's sort of a utility function. This capital allocation line, indeed is a utility function. All right? Well, that is Adam. That's the logic. You do not need to stay with this utility function. You can choose your own utility function, whatever you want. For example, let's say instead of the sigma, put value at risk. All right, then you need a distribution, calculate value at risk for every, well, sort of, well, I mean, here you have the returns, they may be random, then you can have the distribution. In practice, you can calculate the value at risk for any rating scheme, and then you already here. So that would be a different way of, but that is sort of the, I'm in the framework of the MPT, so then I state that. So, well, then the maximization problem probably you know. W1, W2, right? So you maximize the risk, well, the RP with that definition, minus RF with this definition for the variance. And then you know. You can solve it. Right? So you can write the first of the conditions, and find W1 and W2, and then you're good to go. Right? So, well, I mean, let's go through this. Right, so, well, I mean, I just want to find the maximum value. We do this and then we go to a break, okay? So here I want to find where this basically ratio is maximized. All right? So I want the maximum of this capital allocation line. Right? That's the portfolio essentially here. And I can look at the maximum value, all right, that's RP minus the risk-free rate divided by SP hat. So what is the maximum value that we have here? Well, that's the max hat, all right? So now I can plot this essentially line, all right? Well, in some sense, well, I mean, that is sort of, that will be a point, right? So depending on, well, when is ratio of the two, right? Well, look, I mean, this function is not the ratio, right? Well, what I plotted here is just the, on the y-axis that we have this, the returns, on the x-axis that we have the standard deviations, right? Well, of course, we can plot this as a function of well, W1 and W2. Right? But that would be ugly. Right? So people have thought of visualizing this. And well, that's sort of one way of doing this. Right? You can think of this line. Right? Well, look, if I want to maximize this, right, so the ratio will be, well, that guy will always be somehow tangent to this graph. Right? So when you maximize that, then you will actually, the line which is a maximum will be tangent to this graph at a specific point. All right? Well, I could do maybe you shouldn't do the math, the optimization, but let's basically look at lines. So here I will generate some values, I will call them as scan. So that will be an NP range, and well, let's just start at 0 and then go to n, right? Well, I've played with this so that it's indeed nice. We're nicely looking at it, right? So that's some escape, right? Some values which are on the x-axis in this basically plane, right? But don't ask me why I'm doing it. It's just for visualization purposes. It doesn't matter. That makes it essentially easy. And then, well, let's draw a line. So let's call it the capital allocation line, which of course you know the theory for. Well, the capital allocation line will have an intercept which is the same as the risk-free rate. You know that from the theory. But do you? But let me draw it and then you start talking. And let's say we have the max cal and then multiplied by this cal. And so you will know what I mean. And I will plot this scatter. And then the plot of, let's put this cal here on the y-axis. And the cal line I will put there. And let's choose a color of red, and then have the line width. That doesn't matter. Alright. Let me just plot this. Alright, so let's make up a little magic. Well, so this is the red one is called the capital allocation line. Right. So it has an intercept of 6%. Alright, so that's the risk-free rate. So which means that if, well, I mean, you remember the x-axis was the standard deviation. So if I want 0% risk, right, then I go allocate all of my funds in the risk-free fund, risk-free basically rate. So I will basically get 6%. Right. So, but now let's say I want to indeed deviate from this riskless investment. Right? So it means that along this line that I move here. Right? So that's sort of like go and then increase it. Right? And then sort of for every point which I have on this red line, then I'm going to have essentially what was a little bit in the risk-free asset, right? So some fraction. And then there will be some sort of combination that I have from the risky assets. Right? So indeed, if I choose a point on this, then I will have a combination of the risky assets on the blue one. Right? If I go on the red, then it will be a combination of the riskless asset, which is a risk-free rate, and well, risky assets. Right? So if I come to the point where the red and the blue are tangent to each other, then will be the point where this utility function is maximum. When these two lines meet each other, then will be the point where this quantity is maximum. And that is also, you know it as the Sharp ratio. So that's the Sharp ratio.
Sharp
the
ratio.
maximum at the tangent point of this. So now numerically I can go and find the tangent point, of course. Well, I already know how it looks like, but then, well, that's actually not a big deal. Just to find what is the weighting scheme that generates this tangents. So that's sort of, that becomes the point where I have the maximum. For these, basically, assets. All right, but let's, so that's the, well, that's sort of numerical stuff. So let's call these efficient, frontier, and the cow. So basically find this. Alright. So, well, I mean, this is called capital allocation line because you always stay on this red. Right? So if you are above or below it, then you are sort of deviate from optimality of combining the risky assets and the riskless one. So on the red one, then we are sort of on what markets indicate, so are good to do. Right? So let me save this maybe later, but what we can do is to do this not numerically, rather, well, that was numerical. So we generated all this and then maximize that. You can do it analytically, in that you find the first order conditions and so on and so forth. Or you could do this maximization using, well, Python. Yeah, so that's sort of the next step that I want to do. Do the maximization in Python by hand. We have done optimization. So we just use them to solve this.